everyone, and welcome to our last and final slide in this unit, Chapter 4. Let's get started. The title for today is Basic Understanding of Polygons and Circles. The goal is to get ready for high-level geometry and wrapping up Unit 4. In this lesson, we will understand the related concepts such as polygons, polygons, circles, and sectors, and being able to find the central angle of a sector according to the relationship between the sector and the circle. Let me start with a question. Are there any familiar shapes in this picture? What about these? What are some 2D shapes we've learned about? Let's get started with our first section, polygons. Triangles, quadrilaterals, pentagons, hexagons, they're all called polygons. Think, what type of lines or other shapes are these shapes composed of? What do you think is a polygon? What's the definition of it? What makes them polygons? What do they have in common? Here are some polygon-related concepts. First, it's a closed plane figure composed of several line segments not on the same line successfully connected to each other is called a polygon. So a polygon has to be a closed plane figure, and remember it has to be a plane figure, it's not 3D. A closed plane figure composed of several line segments not on the same line successively connect to each other. That's a polygon. It's also line segments that make up the polygon is called the sides of the polygon. For example, these red lines right here, this one segment right here, those are all called sides of that polygon they belong to. Another one is that they're the common point of every two adjacent sides is called the vertex of a polygon, and in a polygon, the line segment connecting two non-adjacent vertices are called the diagonal of the polygon. For example, the diagonal would be this is a pentagon, this is pretty bad, but just think of it as a polygon. And then this would be the line segment. Each of these would be, these would be the sides. Each of these points where they connect would be the vertexes. This whole thing is called a polygon. It's several line segments on the same plane connected, which is called a polygon, and it's closed. And say I had this line connecting this vertex to this vertex. So this line that connected this imaginary line that connected these two vertexes would be called the diagonal of a polygon, and there's many diagonals in a polygon sometimes. Notice, the polygons we usually refer to are convex polygons. That is, the polygons are always on the same side of the straight line where any side is located. Let me explain. So, with polygons, there are two types of polygons. One is called convex polygons, and the other one is called concave polygons. Convex polygons are shapes like this, polygons like this, polygons like this. Okay, so this first one would be a convex polygon. But the second one right here would be called concave. Do you see how one of the vertices, instead of jutting out, it juts inward into the shape? It caves in. That means it would be a concave polygon. So, right now I am displaying 6 figures right here. And I want you to tell me which of these figures are polygons. The answer is that figures 1 and 4 are polygons. Let's go over them. 1 is a polygon because it's made up of multiple line segments and it is closed and on the same plane. 2, it's made of several line segments and everything, but it's not closed, it's open. So that wouldn't make sense. 3, as you can see, it is also open, there's a little crack there. And the line segments, it's not even line segments. Or they might be, but the line segments has to successively or just connect each other. They can't make it open or they can't go over each other. So they have to connect perfectly. 4 is a polygon, same thing as 1, and number 5 is not, because there's no interior space. It's just two lines intersecting each other. And 6, it's not a line segment. There's 3 line segments, yes, but one side, the green highlighted side, is not a line segment because it is not straight. It is a curved side. As shown in this polygon figure right here, the polygon ABCDE, point AB, etc. are the vertices of the polygon. So these points where the line segments intersect are the vertices. Vertices or something. Vertices. Line segments AB and BC, etc., are the sides of the polygon, and angle AB, angle B, etc., are the interior angles of the polygon, referred to as the angle of the polygon. Such as line segments AC and AD are the diagonals of the polygon. Angle AD right here, angle AC, these two line segments are connecting them are called the diagonals because the points are being connected aren't right next to each other. Can you still draw other diagonal lines in the pentagon? Let's draw some other few. For example, we see that we can connect point E and point B to that, point E and point C, point B and point D, and yeah, and you might have seen that that makes up a perfect star. Exploration 1, the relationship between the sides, vertices, and the interior angles of a polygon. So right here, we have a table. And as you can also see, there is 5 shapes shown. What we're going to do is fill in the values together of this table. Up here is the name of the polygon: triangle, quadrilateral, pentagon, hexagon, octagon, and you don't have to care about these 2 parts from now on. At least, not right now. So, let me ask you, how much vertices does the triangle have? 3. Sides, 3, and interior angles. Quadrilateral, 4, 4, 4. 5, 5, 5 for the pentagon, hexagon 6, 6, 6, octagon 8, 8, 8. We keep going on for that. For the heptagon, nonagon, decigon, something like that. We keep going up till we reach something called the n-agon. What does this mean? A polygon with n sides. We don't know how much sides it is. It's an n-agon. So how much will the n-agon have? We'll have n vertices, n sides, and n angles. Conclusion: the n-agon will have n vertices, n sides, and n interior angles. Do you agree with this? Because this n right here is a variable. And this, we have made a pattern out of these regular polygons. We knew that the value of how much vertices, sides, and interior angles were all the same. So, there it is. That's the pattern. Exploration 2. The relationship between a polygon side and the diagonal. I have 2 questions for you. Question 1 is, how many diagonals are there across each vertex of the n-sided polygon, and how many triangles can it be divided into? Question number 2 is, how many diagonals are there in an n-sided shape? So pause the video. I want you to solve these questions on your own. And one helpful hint from me is to use that table again, change up the values a bit, and see what pattern you get. All done? What did you get? So here I have made a table, and we're going to fill in it all over again. Let's see. So number of sides, 4, 5, 6, 7, and of course n, and number of diagonals per vertex. Let's look at the quadrilateral first. From one vertex, how much can there be from one vertex? Well, there can only be one, because the other two, well, they will be connected. It wouldn't be a diagonal then. So it can only connect to its opposite vertex, which is just one way. And the rest is 1, 2, 3, 4. Do you start getting a pattern here? Then, number of triangles it can be divided into. 2, 3, 4, 5. As you can see, there's 2 triangles here, 3 triangles here, 4 triangles here, 5 triangles here. So, what pattern do we get again? The n minus 2. So what is the total number of diagonals that I can have? 2. There's would be 1 here, 2 here. Over here it would be 5. 1, 2, 3, 4. And then 5. 1, 2, 3, 4, and then here is a 5. That will make up a perfect star, which is 5 stars, yes. And then for the hexagon and the heptagons, it would be 9 and 14. So what is it for n? How do we find is n times the difference of n and 3 over 2. So now I want to observe the following 4 polygons. What are the characteristics of their angles? What about their angles do you notice? What relationships do they have? You may have noticed that this is all the definition of the regular polygon. What is a regular polygon? Well, a polygon with equal sides and equal angles is called a regular polygon. Jot that down on your notepad. I think of this when you say the word regular from regular polygon, because these are the shapes. It might not be for you, but to me, and I think for most people, these are the shapes. Like when you say triangle, you might think of an equilateral triangle. When somebody says pentagon, you think of this type of pentagon. When somebody says square, well, there's a square, of course. Or, yeah, or maybe when there's a hexagon, you probably think of this type of hexagon, which is called the regular hexagon. Now let's move on to circles. Look at these 4 pictures. What do you see? Maybe you see a fan, a CD, a penny, and a wheel. Question 1. Are there any figures you are familiar with in the picture above? What do you see? Any figures? Any familiar shapes? What do you see? Question number 2. How can you draw a circle? Well, as you can see, for me, I see many figures with that's either has circles, is a circle, and I also see rounded sides. And those are called sectors because they're part of a circle actually. There's a piece of a circle, but we'll get into that later. And how can you draw a circle? Well, you could trace around it, around object. You could, Here's some circle-related concepts. So, on the plane, a line segment OA rotates around its fixed point O, and the figure formed by the other end is called a circle. So, as you can see, a circle, you should know what a circle is. A circle is the figure formed when you have a line segment and it rotates around one point fully 360 degrees. That is called a circle. The fixed point O is called the center of the circle, and the parts between any 2 points, like A and B on a circle, it is called an arc. So this blue highlight point right here, it's curved, almost like a line segment, but bent. It's called an arc, and it can be represented this way. So the 2 points under with an arc drawn on top. And it is read as arc AB. The figure formed by arc AB and the two radii, OB and OA, passing through the end of this arc is a sector. So this highlighted yellow part right here, made up by the arc and two line segments that you might know as radius, is called a sector, or a part of a circle, and the angle with the vertex at the center of the circle is called the central angle. So let's do some practice. As shown in the figure, the following circles, angle AOB is a central. So from which of these circles is the angle AOB the central circle? Well, let's go over them. Angle A, angle in the figure A, angle AOB, has a vertex from the vertex of the circle. So angle A would work, and we know that that's the answer. But we can't be sure yet because we still have to check others. Well, look at this. B, angle AOB, the vertex of this angle doesn't line with C. So no, this is incorrect. The same with C, and this angle, it's at the edge of the circle, but it doesn't even overlap this O right here of the angle. It doesn't line up with the vertex of the central of the circle. So D is also incorrect, and the answer is A. Now it's class summary, and I like you to pay attention to these because it kind of refreshes our mind a bit. And if you have anything like, what did we learn in this lesson again? This is the time to review. So we learned all about the basic understanding of polygons or circles, and it's mostly preparing you for the later geometry chapters, which it gets harder and harder. So there was two main elements, which was polygons and circles, and we learned about, in polygons, the diagonal of the polygon, regular polygons, diagonal of the inside polygon, and split triangles. And for circles, we learned about central angles and the area of a sector. Well, what skills did we work on today? We understood the relationships such as polygons, regular polygons, circles, and sectors, the basic concepts, and being able to find the central angle of a sector according to the relationship between the sector and the circle. So I hope you enjoyed learning all about chapter 4. And in chapter 5, you'll be introduced to a lot new things. So be excited for that, and we'll see you next time. Stay inquisitive.